I want to come back briefly to the concept of phenotyping, which is about resource characterization. And we have seen a lot about remote sensing, and that really had changed the game in the last 5-10 years. About the amount of detail we can describe a tree with, and the number of trees we can describe that at level. Dependent of that is you've got an enormous amount of data. You need models to make sense of it, and that's the models that, for example, Max has been talking about. So you can extract patterns out of the data and make predictions thanks to those patterns. Another aspect is real-time monitoring of the resource, and to establish sensor networks that gives you a dynamic feedback on how the resource is evolving, and also gives you information about the inside of the tree, how it's functioning. And the pendant is you can use multi-physics and biological models to simulate the way the resource is transforming, and that's really splitting that graph in two. One is the state of your resource, and the other is about how it's changing. So one of the studies done during the last 6 years with a physiological model was done by Damien. He used that model called Kabbalah, developed by Mike Battaglia from CSIRO Hobart. And the model was used to evaluate the impact of site treatments on forest productivity. And he showed that for some sites you would not increase productivity by much, but for other sites you could increase up to 50%. People like to oppose the process-based model to data-driven models. They can complement each other. Data-driven models can help obtaining better parameters of the physiological process, and the physiological processes allow you to understand why a factor is a key factor and what's the mechanism attached to it. And once you are using a physiological model, you get access to a lot more, like the amount of water that the forest is using, the way the carbon is cycling from the foliage to the soil. You can investigate pathogen tree interactions, and so on. At the other end of the physical scales, we have done a study of wood formation across New Zealand using another model coming from Australia called Cambium. So it models the way that the cells develop in a tree by dividing, expanding, thickening their wall, and that's where your carbon is going eventually. So we recreated by simulation profiles of density and ring width for 16 positions in the country. And we found that on the best sites where we had the best data collected on site, we could get down to 10%. So we can predict wood quality with reasonable accuracy across the country. This is for one genotype, but in the process of doing this study, we developed a framework where we can calibrate other genotypes in exactly the same way. In between those two scales, we've got the tree stem, and if you're into timber engineering, that's really what you care about. So this is a tree growing, and you're stepping backwards. As it grows a bit faster than a real tree, barely. So we go up to 7 years, and the tree is composed of growth layers that were formed at different years. So we got year 1, 2, 3, 4, 5, 6 here. The wood that formed each year was influenced by the environmental conditions that were predominant during the year. And when you put back those growth layers together, what you get is basically your wood structure and the distribution of wood properties inside your tree. So that's the tree stem formation model that Peter has been talking about in introduction. Not again. So you get, in the end, same thing as with the DISBot, high-resolution 3D maps of wood properties that are essential for wood processors. We obtain those maps by simulating key transport processes for wood and carbon within the tree. And it can be used as a decision support, for example, how to the sawmill pattern to extract boards out of a given log. But enough with models. Let's talk about real-time monitoring with sensors. This is a small tree in southern Kangaroo, that is part of the accelerator trials that Damien will introduce later. It's equipped with subflow meters that gives you the amount of water traversing the tree during the day. Every 15 minutes, you get the speed of water. So So at night, the water is not moving, it's being evaporating during the day. You can see the pattern, and you've got the pattern for 2 clones. There's another sensor called the dendrometer that is as if you had your finger on the surface of the tree, and every day as the water is moving, the stem is contracting, and you can feel that. It's only 100 microns, but the sensor can sense that. And every night you go a bit further because the tree is growing. There are events where the tree keeps growing and is not shrinking during the day, and that's because it's been raining. And the third sensor that we have and give us the amount of water available to the tree to grow is the soil moisture probe. So we've got the pool of water at the bottom, the amount of water transiting, and also the water reserves in the stem, and that gives us a full picture of the water budget for a tree. At the same time, we get growth. Just because we can look at the short-term response of growth to the environment, we can also, doesn't mean that we cannot look at long-term trends. That's the 4th year of growth in radius, in ring width, for 8 genotypes, 6 trees each. The bold bar is the median of those 6 trees, and we can see there are differences between the genotypes, but for each genotype, there are also a lot of variation. Some trees do very well, some not so well. We can explain some of the differences between genotypes thanks to their, we can explain it by their resistance to a pathogen, here Dophystroma. For example, the AC hybrid was very poorly resistant. Almost all the trees were infected to 90% of their foliage, and as a result, the trees in general grew poorly. Some of the genotypes, like C31, were more resistant than the others, but in terms of growth, it didn't translate well. So sometimes it's a good explanation. Sometimes you need to look at other factors in the microsite to explain why the growth is changing. This was a study to put together experimental data and mathematical modeling as a proof of concept. We used a mathematical model of carbon flow within the tree, which from a point of view of fluid dynamics is rather complex, but we wanted to use it on a real tree rather than an idealistic system. The carbon is flowing through those cells called sieve cells. So we also did an anatomical study of the tissue. We used terrestrial LiDAR and computational geometry algorithms to reconstruct the bottom part of the tree. Thanks to that, we can show that theoretical biology is not something that exists just to write papers, but can have practical application and be helpful in the future for precision forestry. For example, to study foliage growth interactions, or to measure the amount of carbon being pumped into the soils, which is quite important for sequestration. Right. So if we put all those things together, the data-driven models, the remote sensing, sensor networks, and biological and physical models, we can start thinking about creating a virtual replica of the tree, a digital twin. And combined with a lifetime monitoring of the resource, we can develop better models by checking how the model is comparing to the real tree. But we can also project interventions in the model and see what are the growth trajectory and what is the best for you. So we can start thinking about the tree not as something that you plant, but as something that you